Hi, in this module, I'm going to present the formal definition of Bayesian networks, give a few examples, and then talk about a really interesting property called explaining away. So before we begin, I want to review some basic probability. So suppose we have some random variables. We have one called S, which is representing whether there's sunshine, and another random variable called R, which represents whether there's rain. So you should think about a setting of values to S and R as capturing some state of the world. So we don't know which state of the world we're in, so we're going to capture this uncertainty using a joint distribution. So the joint distribution over S and R, written PS comma R, is equal to a table, and this table specifies for every possible assignment to S and R, I'm going to have a probability associated with it. So for example, there's the probability of no sun and no rain is 0.2, no sun and rain is 0.08, and so on and so forth. So notice that I'm using lowercase letters to denote values and uppercase letters to denote the random variables. And also notice that this quantity is a number, it's a probability, whereas this quantity is a table. So the joint distribution captures everything that you really want to know. You can think about it as a probabilistic database that captures how the world works. So now we can use the joint distribution to answer all sorts of interesting questions. So we can compute what is called a marginal distribution. So the idea here is that suppose I'm interested in only whether it's sunshine or not. I don't care about whether it's raining or not. So we can compute P of S, and this is a table which specifies the possible values of S, 0 and 1, and the probability, the marginal probability of that particular value. So how do we compute this? We simply aggregate rows. So in particular, we're going to look at S equals 0, look at the joint distribution and match all the rows where S is 0, so these two, and add them up. So that gives us 0.28. And then for S equals 1, the matching rows are these last two rows, and that gives us 0.72. That's the marginal distribution over S. So there's also another concept called conditional distribution. And here the idea is that suppose I knew it was raining. So I'm going to condition on R equals 1. So now I want to know what is the probability of sunshine. So this is a table where I again specify the possible values of S, 0 and 1, and I want to know the probability, the conditional probability of S given R equals 1. So the way I want to approach conditional distribution is as follows. I have this condition, R equals 1. That means I'm going to effectively remove all the rows where R does not equal 1. So I'm left with these two. And now I'm going to simply normalize this distribution. So I have 0.08 and 0.02. The sum is 0.1, so I divide by that sum, and that's going to give me 0.8 and 0.2 for the values of S given R equals 1. So all I did was select the rows that match the condition and normalize to get the distribution. And now just a simple note is that the normalization constant, which is the sum of these two, is actually the probability of R equals, the marginal probability of R equals 1. And you can check that the conditional, by definition, is equal to the joint divided by the marginal of the thing conditioning on. So let's expand our example a little bit. So suppose we have variables now, sunshine, rain, traffic, and autumn. So we have a joint distribution over all 4 variables, and we can, marginal and conditioning are not mutually exclusive. We can actually define questions that involve both. So here is an example. Suppose I know that there's traffic and that we're in the autumn quarter. And now we're interested in a particular query variable, in this case R. So this question can be written as follows. The probability of the query variable R condition on this evidence, t equals 1, a equals 1. Okay, so now the variables which are not mentioned here are said to be marginalized out. So s is not mentioned here, so we're marginalizing out s. Okay, so in general, there's three sets of variables: the query variables, the conditioning variables, and the marginalized out variables, which form a participant of all the variables in your system. So now let's turn to a classic puzzle, which we will solve using Bayesian. Suppose that in the world, there are unfortunate things such as earthquakes and burglaries, and suppose that they're independent events and hopefully rare. Each of them happens with probability epsilon. Probability epsilon is some small. You've installed an alarm which will go off whenever either there's an earthquake or there's a burglary. So you got some special deal where it's like a 2-in-1 kind of alarm. So suppose you're away on vacation and then you got a notification that your alarm went off. Okay. So now, does hearing that there's an earthquake on the radio or in your newsfeed increase, decrease, or keep constant the probability of burglary? Okay, so does knowing that there's an earthquake in addition to alarm, how does that change your beliefs about burglary? So now we could try to intuit the answer, and I would encourage you to do that and see if you're right. But sometimes this is can be very slippery because the right answer could be counterintuitive. So you might think that because, well, earthquakes and burglaries, I said they're independent. So knowing that there's an earthquake, why should that change the probability of burglary? So that's one way to think about it, but that turns out to be wrong. And I'll show you why. So let's try to tackle this problem using Bayesian networks. So we're going to define a joint distribution over earthquake, burglary, and alarm. I'll do this in the next slide. But first, let's talk about the questions. Let's convert this word problem into mathematical notation here. So the two things I want to compare is, what is the probability of there being a burglary given only that I heard an alarm? Versus, what is the probability of a burglary given that I heard an alarm and I heard that there's an earthquake? So is it smaller? Is it the same? Is it larger? And that's what I want to know. So now let us define the Bayesian network completely. So there's going to be 4 steps to thinking about how to define a Bayesian network. First of all, let's figure out what the variables are. So the variables are whether there's a burglary, B, whether there's an earthquake, E, and whether there's the alarm went off or not, A. Okay. Second, what we're going to do is to model the dependencies between these variables using directed arrows. And these capture, you can think about them as capturing causality, but although that's not necessarily the case here. And so these are meant to just capture qualitative relationships. So here, the alarm is triggered off either by the burglary or an earthquake. So that seems sensible. So to make this qualitative relationships quantitative, I'm going to define a local conditional distribution for each variable conditioned on its parents. So let's go through these examples. So we have B, that's a variable. So a local conditional distribution specifies for each possible value of B, what is its probability? So I said that the probability of burglary is epsilon, and that means the probability of no burglary is 1 minus epsilon. Then we look at E. E has no parents as well, so the probability of earthquake is epsilon, and the probability of no earthquake is 1 minus epsilon. So now let's turn into the, and I can write these conditional distributions as follows as well. So I can write probability of B is epsilon times the indicator of B equals 1, plus 1 minus epsilon times the indicator of B equals 0. So if I plug in 1 here, then I'm going to get epsilon. And if I plug in 0, I'm going to get 1 minus epsilon. And same with probability of epsilon, E. So now, what is the probability of A given its parents? So it's easiest to write it actually mathematically like this. So this is just the indicator of whether A equals B or E. So this is a deterministic relationship, but I've lifted this to this probabilistic notation via the. I can also write this out as a table where I specify for every possible configuration of the parents and of A itself, what is its probability. So here if B and E are 0, and does A equal, is 0 equal A 0 or 0? That's yes, so this probability is 1. Does 0 or 0 equal 1? The answer is no, so that's a 0. Does 0 or 1 equal 0? That's also a no. And does 0 or 1 equal 1? The answer is yes, so that's a 1. Go on the rest of the table analogously. Okay, so now I have defined a local conditional distribution for each variable given its parents. And now the final step is to multiply all these together, and that is defined as the joint distribution over all the random variables. So notice that I'm deliberately using two types of p here. So one is lowercase p, which is used to specify the local conditional probabilities, and the blackboard uppercase p is reserved for the joint distribution and also derived marginal and conditional distributions. So notice that again, that these local conditional distributions are just defined, whereas this joint distribution is derived from the local conditional distribution. All right, so the joint distribution, like I said, is simply the product of all the local conditional distributions. So if I work that out, I get this table over all possible assignments to B, E, and A and its probability. Okay, so now I can work on these questions that I'm asking. So this is my probabilistic database. Let's go query it. So let's warm up with something relatively simple. So probability, what is the marginal probability of B equals 1 here? Okay, so remember, how do I compute marginal probability? I look at B equals 1. Okay, so that selects these rows down here, and I simply add up these probabilities. So there's epsilon times 1 minus epsilon, and then adding epsilon squared. So that gives me epsilon minus epsilon squared plus epsilon squared equals epsilon. Okay, so what about probability of burglary conditioned on the alarm? So remember, for conditional distributions, I'm going to now wipe out all the rows where A is not 1. So I'm left with all these rows which are consistent with my evidence of A equals 1. And now I'm going to look at probability of B equals 1. So that are these two rows. And now I add epsilon 1 minus epsilon plus epsilon squared. Okay, and I'm going to divide by the sum of all these three things, which is the same as the numerator plus this additional 1 minus epsilon times epsilon. If you do the math here, you get 1 over 2 minus epsilon. Okay, so this intuitively makes sense. The prior probability of a burglary is small, but if I hear alarm, then this goes up to actually a little bit over 50%. So now the final question is, what is the probability of burglary given that I heard the alarm and also I hear that there's an earthquake? Okay, so I'm conditioning on now A equals 1 and E equals 1. So I'm going to wipe out the rows where E is 0. And now I am left with, what's the probability of E equals 1? So that is epsilon squared divided by the sum over these two probabilities, which is epsilon squared plus 1 minus epsilon times epsilon. And this gives me, if you do the math, it gives me epsilon. Okay, so this answers our question. Now, when I heard the alarm, the probability of a burglary goes up, rightfully. But now I see that if there is an earthquake, or hear that there's an earthquake, the probability goes down back to epsilon. Okay, so the answer to the question is that observing the earthquake does cause the probability of burglary to go down. Okay, so let me actually work, convince you of this via this demo. So here, remember from this before that we can define arbitrary factor graphs, including Bayesian networks, using this tool. So we have three variables, B, E, and A. Epsilon we're setting to 0.05 here. I'm going to define factors or local conditional distributions here. Probability of B, probability of E, probability of A given B and E. And now I'm going to ask for the probability of B. So if I step through this algorithm, I see that the probability of B is 0.05, which is epsilon. So now what happens when I condition on A? When I condition on A, I find that the probability of B conditioned on E equals 1 is 0.51. So remember, this is 1 over 2 minus epsilon. So now, finally, I'm going to condition on earthquake here. So if I condition on earthquake, then I see that the probability of burglary goes down to 0.05, which is epsilon. Okay, so what do I learn? What have we learned from this? So you can write a flashy headline saying earthquakes decrease burglaries. Okay, so of course this is run a little bit tongue-in-cheek because this is actually not a causal statement. You have to be, because if you go in and cause some earthquakes, I don't know how you would do that, but supposing you do, then it's not like all the burglars are going to disappear. So here decrease does not mean causally effect. It just means that given this evidence, then actually the probability of various other variables change. So the punchline here is that dealing with all these probabilities and reasoning uncertainty is quite slippery. So we need some sort of sound mathematical framework, such as Bayesian networks, to deliver the right answers. So this type of phenomenon is so important to Bayesian networks that it has a special name. It's called explaining away. So in general, explaining away is when you have two causes or more that positively influence an effect. So condition on the effect, further conditioning on one cause, it actually reduces the probability of the other cause. So mathematically, this is written as probability of the other cause given the effect and one of the causes is less than the probability of the cause given just the effect alone. And this is true even if the causes are independent, which might be somewhat of the counterintuitive effect. And this is kind of the hallmark of Bayesian networks. This is called a V structure. It looks like a V. So you can rationalize this if you want some intuition as follows. So you have this effect, and you observe A equals 1. And now you're trying to seek an explanation for what caused this effect. Is it B or E? So just condition on A, well, it could be either one, so it's kind of like 50-50. But if if I told you that one of the causes was actually activated, then that intuitively lessens the responsibility, and you don't really need this other cause to explain A. So that's why the probability of this other cause goes down. So of course that is very hand-wavy, but you can rest assured that there is rigorous mathematical calculations behind that I just did. Okay, so let's look at another example. This is kind of a toy medical diagnosis problem. So suppose you are coughing and you have itchy eyes. Do you have a cold or something else? So remember there's 4 steps, so let's go through them in turn. So the first step is to write down what are the random variables of interest. So here we have cold, C, allergies, A, cough, H, and itchy eyes, I. Okay, so these are variables, C, A, H, and I. So the second step is to draw arrows between them using prior knowledge. So using a really super crude medical knowledge, I'm going to just declare that, well, cough could be either because of cold or allergies, whereas itchy eyes is generally due to allergies alone, but not cold. So step 3 is I'm going to make this quantitative by defining local conditional distribution. So I'm going to, for each variable, I'm going to write down a local conditional distribution given its parents. So probability of C, C has no parents. Probability of A has no parents. Probability of H given its parents, C and A. And probability of I given its parent, A. Okay, so I'm not going to bother to write down the actual probability distribution on the slide. Step 4 is to multiply all these together to form the joint distribution over all the random variables. And lowercase p is local conditional distribution, blackboard p is the joint distribution. Okay, so now I can ask this, I have this probabilistic database, now I can ask questions about it. So let's warm up, not exactly with this question, but a different question, which is, what is the probability I have a cold if I just were coughing? Okay, so let's look at this demo. So here is a Bayesian network for medical diagnosis where I've defined C, A, H, and I. And now I'm conditioning on H equals 1 and I equals 1. And I'm asking for the probability of C, marginalizing out A. Okay, so I am going to, this a few times, it runs the sum variable elimination algorithm, which don't worry about that for now. And it produces that the probability of C, conditioned on equals 1 and I equals 1, is 0.13. Sorry, this I meant to only condition on H equals 1. So let me do that again, and I get 0.28. So I'm going to write 0.2 here. And now, what is the probability when I condition on both H equals 1 and I equals 1? And actually, I already did this, but I'll just do it again. This is going to be 0.13. Okay. So again, you can rest assured that these calculations were followed faithfully using laws of probability. And one thing I want to point out is that this is another case of explaining away, but slightly disguised. So here's how to think about it. So I condition on I equals 1. So I observe that I have itchy eyes. Okay? So itchy eyes is only connected to A. So that's only going to boost support for A. Even though I don't condition on A, I'm getting more support for A. And now having more support for A, now this is an explaining away why the cough. So now A can explain the cough, which lessens the need for the cold. So that's why the probability of cold actually decreases compared to if I didn't have itchy eye. Okay, so you should be really kind of impressed by this kind of reasoning. It's quite subtle, even for this very small 4-node Bayesian network. And even qualitatively, you might think it's kind of hard to understand what will happen to C. So just imagine if you have a huge Bayesian network and you want to get qualitatively precise answers, you should be glad that we have Bayesian networks that can allow you to answer these questions based on the laws of probability. So now let's define Bayesian networks formally. So a Bayesian network is specified by a set of random variables, generically x1 through xn, and it specifies a directed acyclic graph over these random variables. So that specifies the dependencies qualitatively. And then we specify local conditional distributions for each variable xi given the parents of xi. And when you multiply all of these local conditional distributions together, then you get the joint distribution over all the random variables. Okay, so again, we're using local lowercase p to denote local conditional distributions and blackboard p to denote joint distribution. So now we can look at probabilistic inference more formally as well. So probabilistic inference, you're given as input a Bayesian network specifying this joint distribution. So this is my probabilistic database. I get some evidence where a subset of the variables E has been observed to take on particular values of little e. And I'm interested in a set of query variables Q, which is another set of variables. So now the probabilistic inference produces a probability of Q conditioned on the evidence. And just to be very precise what this means, this is a probability Q equals Q given E equals E for each value little q. For example, if I have in my coffee and I have itchy eyes, if I have a cold, this is expressed as this probabilistic inference question: what is the probability of a cold conditioned on coughing and itchy eyes? So this is a formal definition of probabilistic inference. The bad news is that computing this is actually going to turn out to be very computationally intractable, but we'll see algorithms that can tackle either approximately or special cases of it shortly. So in summary, we've introduced Bayesian networks. It's important to think about the basis of Bayesian networks is based on these random variables, which capture the state of the world. We have directed edges between these variables, which represent directional dependencies. Quantitatively, we define a local conditional distribution for each variable conditioned on its parents, and we multiply all those together to produce a joint distribution. Now, this joint distribution is my probabilistic database, where I can ask questions about the world, and this is the process of probabilistic inference. And hopefully, through the alarm and the medical diagnosis examples, hopefully you can appreciate the framework, which is Bayesian networks, and it captures certain types of reasoning patterns, such as explaining away, which might be intuitive or counterintuitive, but you can rest well at night because this is all based on laws of probability. Okay, so good night.